Algebra 2 one-to-one functions. Today we're going to look at functions, which we know a function, every input is paired with exactly one output. And we're going to look specifically at these functions to determine if every output is paired with exactly one input. In other words, if every x is paired with one y, we know we have a function. But if every y is paired with one x, we have not just a function, but a specific type of function, which we call a one-to-one function. So we have 4 examples of functions here, and we're going to explore those functions using the Desmos graphing calculator. So I have typed in question number 1, f of x equals 1/3 x minus 6, and I've got a graph here of a line. Now, if you would like a table, and I do want one, I'm going to type the plus sign. I clicked on the 2, and I'll type the plus sign and choose table. And then I'll put in some points here just to explore. So let's do -3, -2, -1, 0, 1, 2, 3. That should be sufficient. Now for my y1, I'm going to get rid of that, and I'm going to put f of x1. Be sure to put the 1 so that you'll see the points on the right. So those points are displayed on the graph. So the question is, are any of these y coordinates repeating? And more importantly, are they ever going to repeat? Well, you'll notice that the y coordinates are all different here. And you may also notice that these points are increasing indefinitely. So this number y is going to continue to increase each time. It will never go back down. So there's no chance that a y coordinate will repeat. So what we're going to say for the first problem is I'm going to take a snip of this. If you're on a desktop, you can snip this page. If you're on a phone, you can do a screenshot of this page. But I would like for you, if you can, to put something in here. If you're on a desktop, or you can also do share out and get just your graph, and that'll be okay too. So I'm going to go to my problem, and I'm going to paste that in there. If you can't do either, then just write a description. This is a line, and all the y coordinates are different because the line is increasing. It never decreases, so you could say something like that. So we're going to say this is 1-to-1. Each y value is paired with exactly one x value. Now, something you may have thought about is if it's a line, is every line 1-to-1? Well, no, not every line. If a line is increasing or decreasing, then it will necessarily be 1-to-1, because that means the y values will continue to change as x changes. But if you have a horizontal line, then all the y values are the same number. So for horizontal lines, we do not have a 1-to-1 function because the y values, of course, repeat. All right, let's take a look at question number 2. This time we're looking at a quadratic function, g of x equals x plus 2 squared. So I'm going to go back to my Desmos calculator. I think I'll leave the table. I'm going to change this to g of x. And then I'm going to put x, is it plus 1 or minus 1? I've already forgotten. X plus 1. So we'll put x plus 1, or x plus 2, excuse me, squared. Now down in my table I still have that f, so I'm going to change that to a g so that it knows to use the function g. And so here you'll notice we do have a parabola. Now for the values that are in here, I only have 2 of these repeating, but that's because I chose these x values. If I were to change this 25, for example, let's say I changed the 3 to a -4, it'll add another point to the graph. I could change the 2 to a -5, and you'll have another point in the graph. And so you'll notice 2 of the points here at the top have the same y coordinate of 9, and the 2 here at the x equals -4 and x equals 0, they have a y coordinate of 4. So my x coordinates are different, but my y coordinates are repeating. And the same here at -3 and -1, I have the same y coordinate 1. So as you can see in this table, we have quite a few repeating y coordinates. So this function we would say is not one-to-one. Now I'm going to copy this and snip it and paste it. If you can't do that, just write a description of what you're seeing. So a parabola would basically have repeating y coordinates, because basically every coordinate except for the vertex. Sorry guys, I'm on the wrong screen here. Every coordinate, every point on the graph except for the vertex repeats, has another coordinate pair to go with it. So let's see. So for g of x, we would say the y coordinates are repeating. This is not a one-to-one function. Now, if you recall, in an earlier lesson, we talked about the horizontal line test. And the horizontal line test said if you could draw a horizontal line through that function and it intersects the graph more than once, then that function is not invertible. Well, that's because that function is not one-to-one. So you can kind of use that same horizontal line test in these exercises to determine if the function is one-to-one. When you go back to your line, you could draw as many horizontal lines as you want, but you're never going to have a horizontal line intersect this line more than once. But for the parabola, a horizontal line will intersect in lots of places. So this is not a one-to-one function. The next function we're going to examine is p of x equals cube root of x. Now in Desmos, this is a little challenging to find. You'll notice down here at the bottom there is a keyboard. So click on that keyboard. And then over on the right it says functions. Click on that. And then miscellaneous will open up this screen. So this nth root is what you're going to click on. Now in your root, you do need to put your cube root, and then you'll put your x underneath, and then it'll graph it. Now I've left the same x values here in my table, but now I'm going to put p of x, x1. You got to put that 1 so that it can put these values in. And then I'm going to close that keyboard so you can see better. So now notice that all the y values here are different. Now I don't have them in order anymore, so let's change this back to a 2. I think I'll make this one a 3. So you'll notice these values are negative, these values are positive, and you can see from your graph that your graph is going to continue to go up. So each y value along the curve here is going to be different. There won't be any repeating y's because these y's on the left side, they're going down as you go left. So this function will be one-to-one. So I'm going to go ahead and make a copy of this. And I'm going to paste this into my document. Again, if you don't have the technology to take a screenshot, be sure to write a description of what you're seeing so that you can get credit for this work. So be sure to just paste it in there. All right, so what do we know? Well, this function is one-to-one. All the y values will be different. Question 4, w of x equals the absolute value of x. So in Desmos, you've got actually on your keyboard, you should have the vertical bar, which will produce absolute value symbols. So you can just use that. And the keyboard down here has the symbol as well. So if you want to put it there, you can. All right, so I've got x1. I'm going to leave those. And I'm going to put in w of x1. And it will evaluate and plot those points for me. So you will notice right away that you do have repeating y values. So the 3, the 2, the 1, again, and 3, 2, 1 are down here as well. So this is definitely not a one-to-one function. So I'm going to copy this screen, drop it into my document, and this is my work basically for this problem. So if you are not able to make that copy, just describe what you're seeing. A V-shaped graph, the y-coordinates are repeating. It's basically a function, an even function is always going to be, is going to have repeating y-coordinates. So since this is an even function, the y values repeat. This is not a one-to-one function. So you'll notice we had a parabola a moment ago, and that parabola, the same thing happened. Okay, now we're on to the next part. When a function is one-to-one, then the function is invertible. When a function is not one-to-one, then we can restrict the domain of the function to make it one-to-one. So if you remember in our last lesson, we had some functions that were not one-to-one. They were not invertible. So what we're going to do is take functions that are not one-to-one and restrict their domain so that it will be a function. So what I like to do is go ahead and write the equation of the inverse first, and then use that equation to help me determine what domain makes sense. What I've done here is I have gone ahead and found the inverse of the function k of x, and then we're going to use that to help us restrict our domain of our function k of x. So to start, to find the inverse of the function k of x, I've replaced the k of x with y. Then we, of course, reverse the x and the y. This is the inverse when you reverse the variables. And to solve, I added 4 to both sides of the equation. Next, we'll divide all 3 parts, x, 4, and the 2y squared. Divide each one by 2. And then finally, to get rid of our square on our y, we'll do an inverse operation of square root. So the square root of this entire expression is y. And then just turning that back around and using our function notation, we have k inverse of x, and then that expression. Now, last lesson, we did not actually write these in function notation, and that's because our function was not invertible. But what we're going to do now is convert this function so that it is invertible. So go to your Desmos calculator, and I've got the function k of x in here. And as you can see, this function is not invertible. But what we can do is only include the right half of this parabola. Just don't include the left half, which is decreasing. And the way we do that is we open bracket and we put in the domain x is greater than or equal to. And by the way, just do a greater than and then an equal to, and it'll put the symbol for you. And then put 0, and now I have a function that is invertible. So if you go to your table and put in values for -3, if you put in your function k x1, what it's going to do is it's going to basically leave off these values. These are no longer defined for this function. Only these values will be defined. And so now there will be no repeating y values. We've converted this into a one-to-one function. So the domain of our original function is going to be restricted to x, and I'll just use the brackets since we did the same thing in domain, x such that x, let's use the equation editor, why not? I don't see the brackets in here. So x, yeah, let's get out. X such that x is greater than or equal to, and that is in our equation editor, and then 0. So I've restricted the domain of my function. So now the question is, if this is the restriction on my function, now that will restrict the output of my function in this one. So the question is, what's the domain of this part? So let's go over here to Desmos and let's see. I'm going to see if I can do inverse. Okay, so in Desmos, we can type our inverse of our function, and you don't want to use the same variable. So I did K1. You could just use a whole different variable like f of x. But you do need to type in your function, and then you'll notice that it automatically has restricted this domain of this function to -4 to infinity. And why is that? Well, at -4, if you plug a -4 into this function, you will get a 0 out. If you try to plug in a number below -4 into this function, you will get a negative number out, which will not give you a real number output. So it is automatically restricting this domain for us. So we're going to say our domain for this piece is x such that x is greater than or equal to, and I do need to use my editor to get this symbol, to -4. So the domains, we're going to include those with each piece so that we can kind of point out something. And go back to this original function. The original function k of x had a domain x is greater than or equal to 0. Well, the range of that function, once you've restricted the domain, or even before you restricted it, the range of that function was -4 to infinity, or x greater than or equal to -4. So it kind of makes sense that that's the domain of your inverse. If you reverse your x and your y in your function, you're essentially reversing the domains and the domain and the range of the functions. Question 6. R of x is equal to -x to the 4th power. So looking at Desmos again, I've typed in my function, and as you can see, it is not 1-to-1 because these y values are repeating. So I've made a table. Let's go ahead and put in our function so we can actually see those y values. So I'll do rx1, and it'll give me the y values. So notice the repeating y values here and here. So what I want to do is restrict the function so that I'm only using the right side of this function. So we will restrict the domain. So open bracket, x is greater than or equal to 0, and that will give you just the right side of the function. It's not a parabola, but it does look a lot like one. I think I said parabola, but it's not. It is an even function, though. So again, notice the undefined function. So notice we do need to indicate the restriction on r of x, and I did that by writing x such that x is greater than or equal to 0. And then we found our inverse. The process is the same. Replace your r of x with a y, switch your x and your y, and solve for y. And I'm missing a negative in here, so let's put that back in there. That's negative, and so is this. Now, you may think to yourself, wait a minute, I'm taking the 4th root of a negative number, and that's going to be imaginary. That's not going to work. Actually, it's only a negative number if you put in a positive number for x. If you insert a negative number for x, then it will not be negative. So we're going to have to change our domain for this function to fit the range of our function that we created here. So let's go over here and look at it. We have our function -x to the 4th restricted to x is greater than or equal to 0. Well, what is this range? This range is x less than or equal to 0 because our y less than or equal to 0. So what we're going to do is use x less than or equal to 0 for our restricted function, and that will prevent what I just said. It will prevent us from having a negative value under that 4th root. So we're going to say x is less than or equal to 0 is the domain of our inverse of our function. Question 7, L of x is equal to 1 divided by x squared. So we have a rational function. If you go to your Desmos and type this in. This is L of x. So what I'm going to do is I'm going to use L of x for my name of my function, and you'll notice that the y values are repeating. So the number at the -3, x equals -3, is matching the y value at +3. So again, repeating values. So how can we restrict this? Well, we can use the right side only. And if we do that, we're going to say x is greater than 0. Now, unlike before, we had to say greater than or equal to 0. But in this problem, you can't really have a 0, because at 0, that function is undefined. So we'll just restrict that to x is greater than 0. And now all the y values are different, and they will continue to go down. Even though they get really close to 0, they'll never reach 0. So for our domain, we're going to say x such that x is greater than 0. So we've restricted our domain of L of x. X is greater than 0. So the next thing we'll do is write the equation for the inverse of L of x. So replace your L of x with a y, reverse x and y. So if x is equal to 1 over y squared, you can multiply both sides of the equation by y squared to get xy squared equals 1, and then divide both sides by y squared. So you basically are just switching the x and the y squared to solve for y squared. And then finally, to the inverse operation for squaring is square root. So we'll square root both sides of our equation and get y equals the square root of 1 divided by x. So the domain of our original function was x is greater than 0. It just so happens when you look at this graph, the domain and the range are both greater than 0. So the y's on this graph are all above the x-axis. So y would be greater than 0. So that means the domain for this part is the same. So I'm just going to copy and paste that domain here. So the domain is also greater than 0 for our inverse. Question 8. You can determine if two functions are inverses of each other by using composition of functions. If the functions f and g are inverses of each other, then f of g of x is equal to g of f of x, and both of those would give you the output x. Now think about it this way. F of x, if you plug in an x value, will give you a y value. If you turn around and take that y value and plug it into the inverse of the function, then you'll be back to where you started and get your x value. And that's because the x's and the y's of the functions are just reversed. So let's do the function, the composition of functions to figure out, or show actually, because it does say these are inverses, to show that f and g are inverses. So to start, I will take the function g of x, and I will put the whole function g of x in place of x into the function f of x. So in the function f of x, we have substituted the expression -1/2 x plus 2 in place of the variable x. When you distribute your -2, -2 times -1/2 is just 1, so that gives you 1x, and then -2 times +2 is -4. If you combine like terms, -4 and +4 give you 0. So your output is x. So we have verified that the composition f of g of x is x. Now let's verify that the composition g of f of x is also x. So now we have replaced the x in the function g of x with the expression -2x plus 4. Then we've distributed the -1/2. A -1/2 times -2 is +1, so that gives you +1x. And then 1/2 times 4 is -2, or -1/2 times 4 is -2. And -2 plus 2, this should be a 2, will give you a 0. So the output again is x. So we have verified f of g of x and g of f of x are both x, and that is showing us that the functions f and g are inverse functions. So let's write that. F and g are inverse functions. Question 9. P of x is equal to the square root of x minus 2, and q of x is equal to x squared plus 2. Now on this one, we will need to restrict the domain of q of x because that is a parabola, which we know is not a one-to-one function. So it is restricted 0 to infinity, and of course another way to write that is x is greater than or equal to 0. So first, we're going to do the composition P of q of x, and that means for the x in the first function, we will replace that with our expression x squared plus 2, and then we'll do q of p of x. And so in this case, we will replace the x in the function q of x with the square root of x minus 2, and then we'll simplify each one to show that they do simplify to give us the expression x. Okay, so now I've typed the functions p of x and q of x into the Desmos graphing calculator, and you'll notice that the domain of p of x was automatically restricted to be values of 2 and greater, and that's because if you go below 2, the number under that square root will become negative. So you don't technically need to restrict that domain, but now you can really see why it's necessary to restrict the domain of q of x. Because it's not a one-to-one function, of course, and we do want to restrict the values so that it looks pretty much like the graph of p of x, but reflected over the line y is equal to x. So I'm going to add a third row and put y equals x, and this is a line on my graph, and I'm going to adjust with this tool and make this a dashed line. I think I'll make it orange. And so you'll see that I want this function p of x and q of x to be reflected over that line. So what I really want is just the right side of my parabola here. So let's restrict this domain by typing a domain x greater than or equal to 0. And now you can see that the domain of that domain for our function q of x makes those two pieces look the same. They're the same shape. They're just reflected over the line y is equal to x. So what I've done in here is I've put the restriction, and I went ahead and put on here the restriction on the p of x that was already there. I didn't have to put it in my graph, but the values for x are only going to be, or give us function values when x is greater than or equal to 2. So next I did the composition of functions. So to do that, we'll take the function q of x, which is x squared plus 2, and we'll replace the x in the p of x with x squared plus 2. When you do that, the plus 2 and the minus 2 have a sum of 0, so you get the square root of x squared, which is actually plus or minus x, but we're only using the positive values for x here, so we'll say x. And then on the other one, q of p of x, we'll take this x in the function q of x and replace it with this expression, the square root of x minus 2. So when you put the square root of x minus 2 in for x and square that expression, it removes the square root symbol, and you're just left with x minus 2, and then of course plus 2 would give you an x. So p of q of x and q of p of x both produced an x. So these are inverse functions. So now we're to the last problem, and we're going to type our functions into the Desmos calculator to kind of get a look at our two functions. You can kind of see that they're inverses before you even do the work. So a of x is equal to the quantity x minus 3 cubed, and then the other function was b of x, which is cube root of x plus 3. So to get cube root, click on the keyboard down at the bottom, click on functions, and then nth root, and then you can change this to cube root of x. And then what do we need after that? We need a plus 3. Okay, so these are our two functions. I'm going to hide my keyboard. Now to verify that these are inverse functions, we will take the variable x in the first function and replace it with the expression cube root of x plus 3. And then we will take the variable x in the second function and replace it with the expression x minus 3 quantity cubed, and we will show that both of those give an output of x. So for a of b of x, we have replaced the x with the expression x cubed plus 3. And then we combine like terms in the parentheses. A positive 3 and a negative 3 is 0. So we get the cube root of x cubed. And those are inverse operations, so that removes our cube root and gives us an x. To do it the other way, we take the function a of x, which is the quantity x minus 3 cubed. We replace the x under the cube root with x minus 3 cubed. Cubing and cube rooting are inverse operations, so that just removes your parentheses, removes your radical. You just get x minus 3 and then plus 3. And then opposites, negative 3 and positive 3 give you 0, so you get an output of x. So a of b of x and b of a of x both produced an output of x. Both functions, these functions are inverse functions. Now, you may note that we did not restrict the domain on these functions. So if you go back and look at the graph of the functions, maybe you can see why. Both of these functions are one-to-one functions. So there was no need to restrict the domain of either function. So, in summary of today's lessons, we looked at one-to-one functions. That is a function where every x is paired with one y and every y is paired with one x. We learned how to restrict the domain of our function to create a one-to-one function whenever there's not already a one-to-one function. And then we also looked at graphs of functions and their inverses to see how those two are related. They are reflected over the line y is equal to x. And finally, we did composition of functions, f of g of x and g of f of x. If we get the output x both times, then we know that those functions are inverse functions. Continue to practice. Until we meet again, practice, practice, practice.